Yeah, it is quite interesting. Yeah, we get on every topic. It's an interesting game.
I had that course once upon a time. It was very lame.
Many things.
I'll begin with a word of prayer.
Did you hear what he said about me?
Dear Father, we thank you for this day. Again, I thank you for this class and this time we have to meet and study your creation. Just pray that you'd be glorified what we do, and that we all enjoy the break, which is soon to begin. In your name I pray, Lord Jesus. Amen. All right, lest I forget, here's the exciting attendance sheet. There you go. So I have to talk more about center of mass. So let me remind you. So we want to talk about, today we're going to try to talk about conservation of momentum. But in order to do that, we must understand what we're talking about. And what we're talking about here is a system of, let's say, n particles. And so if we have n particles, so suppose we have masses m1, m2, mn at, position vector r1, position vector r2, position vector rn, then we defined the center of mass position to be equal to 1 over the total mass, big M, and then we had the sum, I equals 1 to n of m sub I, r sub I, like this, right, where big M was equal to the sum I equals 1 to n of m sub I, right? So we defined center of mass like that last time, and I mentioned to you guys that we can also, also we have the center of mass velocity is dr dt. We define that as well. This is the velocity of the center of mass, which is a kind of funny thing to talk about because there doesn't actually have to be a mass there, right? I mean, you could talk about 4 masses that are on, vertices of a square. The center of mass would be the center of the square, and there's no mass maybe actually there, and yet we can talk about its velocity. So it's a theoretical construct, but it's a very useful one we use all the time. And what it allows us to do is to think of a collection of masses as a single mass at the center of mass. And must be another party day in the history department. Kind of rowdy over there. If I was teaching indoor go-karting, this would be an awesome room. Something like that, I don't know. Like indoor go-karting, I should bring in the, I got the, I do have, my children have the, the wheels of the rolly thing you stand on top. What are these? What's that?
The Segways?
It's not a Segway because it doesn't have the stick. It's hoverboard. Yeah, hoverboard. Things just catch on fire, the hoverboards. And so we have, my wife bought them the thing that you can put over it and makes it into like a little go-kart.
Oh, yeah.
And every so often we'll bring them to Liberty and drive around when nobody else is here. It's pretty awesome. But you could totally race those in here, Oh well, maybe I'll bring next time I bring Benjamin, maybe I'll have him bring the hoverboard go-kart thing, and the whole class, he'll just be racing around the perimeter of the room over and over and over again,
I would let him handle slips faster, right?
That's true. That's right. He could go give you guys your tickets properly. So this, of course, is the basic concept of center of mass. We're talking about a finite collection of masses, right? But you can also think about limiting cases here. If we think about, if we allow m sub I to be replaced with a little infinitesimal mass, which is at the position r, then we can define the total mass to actually be the integral of dm. All right, and we can define the center of mass to be 1 over the total mass times the integral of r dm. All right, and this is, the integration is taken over the object. And I'm going to leave that just kind of vague like that. What I'm trying to say is there is a continuous extension of this concept to not just a finite collection of masses, but a continuum of the masses. And if we do consider that kind of scenario, the finite sums here, we pass the limit of the number of masses going to infinity, the summations become integrations, that is continuous sums, and in so doing we can extend the concept of total mass and center of mass to not just a finite collection of mass, but actually an infinite collection of infinitesimal masses. All right. So I have about 4 or 5 calculations in the notes, or calculational setups in the notes about like how this works. And I'm not going to burn up a bunch of class times writing those out. Hopefully at the end of class, the projector hopefully will work, and I will put those up. I'm not going to put them up until then, though, because we're just going to go on. All right, so just a side comment. I don't think I have any homework on that for you guys, but we will come back to the infinitesimal method a little bit later in the course. So it's probably good for us to look at those in terms of calculational setup here. All right, so continuing with my discussion of finitely many masses, we can define the momentum of the system with n masses to be big P is equal to the total mass times the total velocity. All right, and then it becomes an interesting question, is how does the total momentum of the system, how does that relate to the momentum of the masses comprising the system, right? So like, let's look at that. Let's do a calculation and see how they're related. Because they're related in kind of a stupid way. So let's calculate. Yeah. This is not an easy room for that, I tell you. So the total momentum, I was kind of hoping this one works, I get a second shot, but oh well. It's the total mass times, velocity. I'm just writing it down again. But remember, this is the total mass times what? Times d big R dt, right? Yeah. And so that is the total mass times d dt of what? 1 over the total mass, right? Times m1 r1 plus plus m and rn. I'm assuming that you guys prefer me not to use the summation notation. I mean, we could go either way, but I think a lot of times students understand the plus dot dot notation a little bit more efficiently, even though in some sense it's not as rigorous, but whatever. Okay, so then notice that total mass is a constant here. All right, we're not assuming, we're not allowing these masses to change. So these masses, they be canceling, and calculus shows us we've got what? We've got the mass m1 pulls out, so I've got m1 dr1 dt, right? Plus m2 dr2 dt, mn drn dt. But what is this and that and that and that? What are those? I mean, this is exactly the velocity of the first mass. This is the velocity of the second mass. This is the velocity of the nth mass. Right? So what is that then? We have that the total momentum is equal to the momentum of the first mass plus the momentum of the second mass plus the momentum of the nth mass. And there you go. That's how do you find the total momentum of a system of n masses? Well, good news. You just add the momenta of each mass. All right. Now this is all, of course, done with respect to a given coordinate system. If I was to use a moving coordinate system, well, that would change things, right? Because velocity depends on coordinate system for sure. This is all being done with respect to a given fixed frame of reference. Any questions so far? All right, so what did we learn last class? We learned that Newton's second law can be reformulated. Remember? How's it go? Newton's second law for the ith mass is d pi dt equals to, let's say, the net force on the ith particle, right? Let's use that as a notation. Since we're thinking about more than one particle, let me say it's the F net comma I. It's the net force on the ith particle, right? The net force on the ith particle. So, all right. And we've got 1, 2, 3 n particles, right? So I can, if you don't mind, I'm going to use summation notation. That's kind of funny. After what I just said. So the momentum, right, is equal to the sum I equals 1 to n of the momentum of the ith particle, right? So that tells me that dp dt is equal to, using linearity of the derivative, sum I equals 1 to n of dpi. I've changed the summation notation as to confuse more of you. If too many people understand, I'm not doing my job. Some of you could understand too easily, and then you won't need me. So I have to maintain my job security by giving you substandard lecture. Let's see here. So that's mostly a joke. But let's see here. So that, we know by Newton's second law, is this, right? This is the sum I equals 1 to n of the net external force on the ith particle, right? Well, I shouldn't say external force. It's just the net force on the ith particle. All right? Then the question then becomes, all right, so let's talk a little bit more about this. We need to talk a little bit more about this. What is this, though, right? We should try to break that down a little bit more. Let me draw a picture to try to explain what the issue is. So, all right, so I've got like mass 1 here, mass 2 here, mass 3 here for the sake of discussion, all right? I'll just attempt a picture with 3. I think that's enough. It'll serve to illustrate the problem that we're up against. So that one's at R1, this one's at R2, and this one's at R3, right? So if we think about the first mass, in the situation there's 3, what are the forces on mass 1? Well, there could be forces that are involved in the interrelation of the masses, right? So like there could be a force from M2 and M1, something like this, right? So this would, we could say the force of 2 on 1. So here's my notation for this current discussion. Force Ij equals force of the ith mass on the jth mass. All right, so F21 would be there. See, there's also over here, conversely, there's going to be a force acting on M2 of the first mass acting on the second mass, all right? But if we think about it, there's more than just that, right? Because you also have, like, the mass, the third mass, like that. We'd have what, F in my notation, F what of, yeah, 3 comma 1 there. And also, of course, here there's, and I'm assuming that the force from the third mass is somehow directed along the line that connects the mass, but that's, you know, that's kind of the force I have mostly in mind is gravity, right? But you could, in principle, imagine there's little springs connecting the mass and the The springs themselves are pretty massless, but there's like a spring between the masses, and we could think about that kind of thing. Then again, the force would be along the line that connects the masses. Typically, the force is along the line which connects the masses, but I suppose logically speaking, you could consider other things. All right, and then on 3, we'd also have what? Like, we'd have this one, the force of 2 on 3, right? And over here we'd have the force of what? The force of 1 on 3, right? So each one of these 3 masses has 2 forces acting on it from the other 2 masses, right? And then what's the other possibility? We think about all this system collectively as one giant, we can think about this kind of all collectively. It's like, it's some kind of system, right? But you could also have external forces, right? From something outside, right? Like maybe the whole thing is inside a wind, like, there's a fan that's blowing on all of them, and there's a net force like that away from the fan that's blowing on all of them, that kind of thing. That force has nothing to do with the given masses. It's just an external force, right? So in addition, we can think about some kind of like external force on 1, and maybe this is the external force on 2, and for the purpose of my illustration, the external force on 3, right? There's an external force that acts on each mass, right?
Are they all going to be like parallel?
They could be any which way. I mean, maybe
How does the external force act on like one opposite than another?
maybe because maybe they're maybe the external force is actually from like a herd of evil cats that's they're emitting from some dimensional portal at the origin, flowing outward, and as those cats hit the masses, they push them away. If you want a physical example, but no, I don't know. I mean, it could be anything. I don't know what the external force is exactly. It could be, like I was saying, maybe they should all be pulling in the same direction. It's like a fan.
So they're just not related to each other.
Yeah, they're not related to each other. It has nothing to do with an interaction between the masses. It has to do with some external phenomena which is acting on all of the masses, right? It could be gravity. If it was gravity, they should all be like the external force should just be downward, right? But gravity of the Earth has nothing to do with, say, a collection of 3 bowling balls, Like the Earth's gravity is independent of the existence of these 3 bowling balls. To a good approximation. All right, so what I'm trying to tell you guys, and I hope it's a little bit complicated, right? But the net force on the ith one is equal to what? It's equal to the external force on the ith one plus the sum, right, of j not equal to I of f, in my current notation, what? J comma I, right? So you have the external force, and then you also have all of the internal forces, right, which act on that given mass. And so what happens when we take the sum over all of these? What happens here? Right, that's what we came to up in the green boxed equation, right? We found our way to this, but then the question is, what is that? What is that? It actually simplifies quite a bit, because it turns out it has absolutely nothing to do with the internal forces. Why? Explain to me, why is this right here have to work out to 0? You can kind of see it in my hypothetical 3-mass system, right? maybe if I drew my picture right, remember Newton's third law says what? To every action an equal and opposite reaction. These internal forces between the masses, they have to come in third law pairs. So like the force of 2 on 1 has to be equal to minus the force of 1 on 2. They have to be, same magnitude, opposite in direction, right? And as such, these two guys, they'd be canceling. Likewise, F31 and F13 cancels, and F32 and F23 cancels, right? And as you think about this sum, it's a sum of third law pairs. For every I, there's a j. For every j, there's an I. Like, if you think about this sum, they all cancel out. So that sums to 0. And what we're left with is that actually this is equal to F external net. The external net force, which is, by the way, right here. This is the F net external, the net external force, right? So let me record this result for us. What we have then is that dp dt, the change in momentum, is equal to the net external force. Which is exactly the external force on the first one plus the external force on the second one plus plus the external force on the nth one, all summed together. Right? Now, I wrote at the start of this lecture, conservation of momentum. What do we mean when we say something's conserved? What does that mean? It doesn't change, right? The derivative is what? 0. So what would it take for momentum to be conserved here for a system of particles? The what has to be 0? The dp dt has to be 0. How can that happen? I mean, I agree. We need the net. Yeah, we need the net external force to be what? 0. Right? The net external force needs to be 0. But there's a little bit more we could say. Let me rewrite this just a little bit differently in using what you might call the infinitesimal method. We could also express this relation we just found as follows. We could say dp vector, dp vig vector. So dp vig vector is equal to, the external force, the net external force, which I'm just going to call that for the sake of this discussion. All right, so, all right, fine. I just made yet another notation. F external. Oh no. Rats. F external net. All right, so I'm just using that. All right. This times dt. Right? This is another way we could look at what we just derived. So yes, dp would be 0, right? The momentum would not be changing if the net external force is 0. But what's another option? Think about it, right? dp is equal to 0 for the external force equals to 0. Or, how about this? What if dt is equal to 0? Also gives, dp equals to 0. If you don't like me using infinitesimals, and you're certainly within your rights, we could just as well erase these little differentials and say, this really says like the change in p is f external times the change in t for small delta t, right? And then instead of this, I'd write this guy and that guy and that guy. There you go. Now you can show this to your your mathematician friends, and they won't cast you into the outer darkness and so forth. Yeah. So these are two different, possibilities that we could use in order to have the net momentum stay constant. All right. So we'll talk more about this next week. So like well, maybe not next week, but you know what I mean. Here is typical of what we call a collision. A collision is something where we have a collection of masses, right? They come together, they slam together, bang, and then they go flying apart, right? But the time before they come together and they go apart is so small that there's not enough time for there to be a change in momentum. So for a collision, we can conserve momentum because the change in time for the collision is so small, there's simply not time for an external force to really change the net momentum. And then, of course, the other possibility is just, well, the external force really is zero, all right? So, for example, I'll give you guys an example here. We could have like M1 with, say, V naught equals to 10 meters per second, all right, and M1 is 10 kilograms, and then we can have down here M2 equals to 20 kilograms, right, and it's initially got V, let me call that V1, and let's say we got V2 here is 5 meters per second, all right? And just for the sake of discussion, what angle do you guys want me to make? Let's do an angle off the vertical to be different here. Let's make this, did I hear 40 or 30? What do you say? 45 degrees, very lazy, I like it. 45 degrees. These two masses, right, they're moving along, and let's suppose that they're on an ice rink or something, right? They're sliding without friction on some plane, and and they come together later here, and then they get stuck together, right? They glom together M1 and M2 like that. Then the question is, VF equals what, and what's the standard angle of the resulting motion, right? You can already tell if you have a good physical intuition that my picture is not right. Where should VF actually be going? Let me just make it less weird to start with. It should be going like this, right? So let me not be weird and just sort of anticipate the answer should be something like down here somewhere, right? So what's the magnitude? And what's this angle here for the resulting motion, right? Well, let me say it this way. What's the magnitude and what's the standard angle? Magnitude and standard angle for the final velocity here, assuming that they collide, stick together like that, all right? So in this problem, I'm assuming that they're sliding on, like an ice rink or something, and there's no friction, so in short, there's no external force for this mass 1, mass 2 system, right? So I can write down, M1 times V1 plus M2 times V2 is equal to M1 plus M2 times VF, right? What am I doing? This is conservation of momentum in the collision. So I have the momentum of the first one, right? This is P1. Here's P2. P1 plus P2 is equal to the final momentum. All right. Okay, so then we need to figure this out. So we've got what? We got 10 kilograms times, since you guys gave me an easy one, 45 degrees. We got a minus 7.07 meters per second minus, it's going to be plus 7.07 meters per second. There's my V1 vector, right? Because it's, wait a minute. That feels wrong. Care to correct my mistake there? Yeah, I think I need to, move the minus there, right? So let's do that. So we've got, because it's going to the right, right? So it's right and down, so I should have a plus here and a minus over there, maybe that'd be better. Now V2 is easier. V2 is just what? We got what, 20 kilograms, and then we've got ourselves 5 meters per second, comma 0, right? That's all equal to 15 kilograms because mass is neither, wait a minute, what's 20 plus 10? Goodness gracious. It's definitely time for the break. 30 kilograms, maybe.
I agree. We should take a break.
Times VF. you guys are already here. Let's finish this. All right. So, what we got? We've got VF is equal to, if we do this, it looks to me like I've got a 70.7 plus 100 kilogram meters per second for my x component. And then for the y component, minus 70.7 kilogram meters per second. And I got to take all of that and divide by 30 kilograms. So my VF looks like is what do we got here? 100. I got about 5.69 meters per second here. And the other one, I've got about 2.36, there's a minus of course, meters per second there, right? So my final speed is what?
Those two values squared added together, the square root of that.
Yeah, that's what that is at. So we get magnitude 6.159-ish, something like that. There's my final speed. And let's see here, inverse tangent of 2.36 divided by 5.69. I'm in degree mode, so I get at theta equals to minus 22.53 degrees, something like that. So there's the standard angle and the speed, the magnitude of the resulting velocity. Right? And we used what's called conservation of momentum. All right? Any questions? So I can assume, momentum's conserved because there was no friction, right? I said that we were on, these are like, maybe they're like, I don't know, blobs of something, and they blob together. This is a sticky collision, you could call it. We have a more technical name for that, so I need to give you guys a definition of something. So definition, the kinetic energy for a system is simply 1/2 m1 v1 squared, 1/2 m2 v2 squared, 1/2 mn vn squared. In other words, this is a sum of the kinetic energies of m1, m2, mn. All right. So we can talk about the kinetic energy of a system as the sum of the kinetic energy of the masses involved. All right. And so in light of that discussion, we can define two different kinds of collisions. There's two different kinds of collisions. The one kind of collision is a collision where the kinetic energy of the colliding particles, the colliding masses, is conserved. All right? So, definition, if a collision has, number one, the kinetic energy before equals to the kinetic energy after, then it is an elastic collision. Number two, if the kinetic energy before is not equal to the kinetic energy after, then it is an inelastic collision. I would say typically the kinetic energy before is greater than the kinetic energy after, but I suppose you could have a situation where you have like an explosion and chemical energy is released, and that chemical energy is converted into mechanical energy, and as such the net kinetic energy is more after than before. I think, anyway, in my current definition that's still inelastic. It feels a little bit wrong to me, but whatever. Definitely elastic is, everyone agrees, elastic collisions are those which have energy conserved before and after. So my question to you, example 2, was this a elastic or inelastic collision? What do you think? So let's look at, you say inelastic, very good. Let's look at example, was it 1? What's the kinetic energy before? We have 1/2. My first mass was 10 kilograms. My initial velocity was 10 meters per second. You gotta square that guy. And then plus 1/2, 20 kilograms times 5 meters per second. Square that guy. See what that is. What's the kinetic energy after? 1/2, it's like one particle with 30 kilograms. And we found the 6.159 meters per second was the final speed. So we got to do that. So here's the kinetic energy before, the kinetic energy after. Let's calculate these things. What are they? I get 750 joules before. How much after? Sure. I've got 569 joules after. So yeah, so collision was inelastic. All right. Any questions? And why is energy lost in the collision? I mean, I said it's on a frictionless plane, right? So the answer is, like, the process of those two masses coming together and glomming together necessarily has to release sound, heat, things like that. So those are ultimately the answer for, like, where did the energy go? The energy was converted from mechanical energy to energy of some other form, perhaps heat, sound, light, whatever.
Can we calculate if they like bounce off each other? Would we be able to do that?
What if it was an elastic collision? Well, yes, if the collision had been elastic, all right, in other words, they collide according to their given trajectories. think what would happen then is that the resulting motion would be such, so like the net momentum being the same as was given, the net momentum still has to lie along the direction of the line we just found. It still has to be like, the net momentum has to be like that. So we're kind of stuck with that. But if this collision hypothetically was elastic, I don't know for sure. I'm a little fuzzy. I can't remember. There's a result we have that will derive the week after spring break, which is that if we have an elastic collision in the plane, what happens after the collision is they go off at like right angles. But I think that what I'm not remembering is whether or not that result presumed equal mass. It might have presumed equal mass. So if that was the case, then I just really don't know without going through the analysis, which is pretty tough, because to assume, if we're assuming an elastic collision, let me show you what we're up against. We would instead be solving this. We'd be solving M1 V1F plus M2 V2F, right? So we have unknown velocity for the first one, unknown velocity for the second one, right? And what else? That doesn't seem like it's a well-defined problem. This is a two-dimensional vector equation, right? Yeah. So that's two equations, but there's four unknowns because I've got the x and y components of both v1 and v2. But there's more. If we're assuming it's elastic, we also know what? We also know that like Ke initial is equal to Ke final, right? So now all of a sudden I've got three independent equations, but I still got four unknowns. I'm not super confident that that has an answer without further specification. So, yeah. But that's exactly the kind of question we'll be asking after spring break. So there you go. Actually, like assuming the collision is elastic and working it out is a much harder problem, because it involves this, which you might not realize, but if you get into the details here, this is a quadratic equation in the velocity. Momentum, on the other hand, is the handy-dandy linear equation, which we can solve all day long, not a big deal. But the quadratic equations, and you're talking about more than one variable, it gets fussy. Okay, so generically speaking, so I don't think I can answer your question today. Not easily anyway. But elastic collisions are bouncy. They're like perfectly bouncy. Inelastic collisions are typically, they don't have to be perfectly sticky. Like I think the one we just worked, our example one is I believe it's, if I remember the terminology correctly, it's perfectly inelastic. It's a purely inelastic, a totally sticky collision. So when the masses stick together, it's not going to be elastic. Like that's just how things are. Can you guys tell me an example of a nearly elastic collision that you perhaps have seen in your life? Yeah. Playing pool, right. Yeah, billiards is pretty close to nearly elastic. And those, what's that, did I hear curling? Curling? I wouldn't admit to that. Let's see here. Sorry. Curling.
That's what I was thinking of when you first said.
You guys are funny. There was something I was going to say. Ah, man. So a different example, and I won't work out the details. We'll probably do this one after break. But if I had M1 plus M2 stuck together, right, and then they are launched here with velocity v naught. They come up here to the top, right, and then M1 and M2 go their separate ways, and there's like some kind of explosion at the top of the flight. in that case, I couldn't just use conservation of momentum. I couldn't assume that the momentum here is equal to the momentum there. Why? Because there's enough time for the force of gravity to change momentum. So we'd actually have to account for the change in momentum due to the gravitational force acting, going from here to here, and work on that problem like that. So again, we'll probably do an example like that after break. Let me, if it'll allow me, show you the calculations I was going to attempt to show here. And then we'll be on break. Woohoo! All right. So you don't have to write any of this down if you don't want to. These are just the examples from the notes. Dr. Sperano told me he was actually covering moments in Calc 2 this semester, which was kind of interesting and a little bit unusual. These aren't, by the way, what I'm about to show you here, I don't believe these are moments. These are, these are the coordinates of the center of mass. So what other names those have in the literature, I have no idea. Yeah, the centroid is related. Let's see if I can find it.
You were talking about momentum in Calc 2 this morning.
Really?
Yep.
Man, I was not able to pay attention every I thought we were talking about series. Again, you might not be paying
When I first taught Calculus 1, I taught Calculus 1 in summer school. And it was thanks to the fact that some international student didn't take care of his visa issues. So then like the day before, the graduate director was like, James, can you teach Calc 1 this summer? I was like, with pleasure, yes. He's like, great, because no one else could. And I never taught calculus before, but that semester, I covered relativistic momentum in Calculus 1. So it could be more ridiculous. Let's see here. So here we go. Eventually I'll find my way. So what I was saying earlier is that in the case that you have a continuum rather than a finite collection of masses, that the finite sums get elevated to integrals, like this, this, and this. But how you interpret those depends on the context. If you're talking about a one-dimensional distribution of mass, you just make your lambda is dm dx, that's the mass per unit length, and you integrate lambda dx to get the total mass. You integrate lambda x times x. This is x times dm to get the x center of mass. That would be it for one-dimensional problem. Then for a parametrized, for like a space curve, like a helix, for example, if I have the mass per unit arc length like that, I do the arc length integral, integrate lambda over ds. That gives me the total mass of like a path. And that's my x and y and z center of mass. I integrate. The key is just that dm is lambda ds. Lambda could potentially be a function of, it could be different along different points in the curve, right? You could have a wire which has different thickness, and this would take into account more mass being one place than another. You could also have the mass spread over an area. In that case, we usually use sigma for mass per unit area, like this, dm dA. And then I have to integrate sigma dA to get the total mass. I have to integrate x times sigma dA to get the x center of mass, and y times sigma dA to get the y center of mass. So we have to do the appropriate notion of integration to the problem. If you have a surface, which is not just a laminate, like not just a planar area, but actually like maybe it could be a cylinder or a sphere, something else, a monkey saddle, whatever, float your boat. Sigma is dm ds, where ds is the infinitesimal surface area element, which is calculated by the magnitude of the normal vector times du dv, like such. This is Calc 3. And anyway, so again, x center mass, y center mass, z center mass is again found by integrating x, y, and z times dm over the respective proper region. And then finally, if you have a three-dimensional mass, your mass is mass per unit volume, and you have to integrate rho dV to get the total mass, or rho times x dV to get the x center of mass, y center mass, z center mass. And then I actually worked out, so if you have a line segment of constant mass, the center of mass is in the average of the endpoints. Not surprising, right? And this is, if you're in Dr. Sprano's Calc 2, I think he taught this to you guys this semester, to find the x and y center of mass for a rectangle. I did that here. It's in the middle of it. And here I calculate the center of mass for a helix of, this helix is heavier where z is larger. Right, it's got more mass there, and oops, oh man, what just happened? Rats. Anyway, so I work it out, do the integral, and lo and behold, the mass of the helix is that, and its center of mass actually ends up being here. So, oh, and then I did a pyramid. But anyway, again, I don't have any homework problems on these, so yeah. Just in case you care, here's a couple sort of beyond the course examples. I think that's pretty much it. Oh, this one's an interesting example, and I really will stop. This one is very interesting because this shows you, the idea of this example, there's a point mass, an area mass, and a three-dimensional mass. And to find the center of mass for all three of these things taken collectively, what you do is you find the center of mass of each one, and then do a weighted sum of those. So like, I find the center of mass of the one-dimensional, the two-dimensional, the three-dimensional. The total mass times this gives me the center of mass of the whole system. So what I'm trying to say is you can stack these concepts and do kind of more exciting, complicated examples. But again, I have not made good on this threat in my homework, so you're probably safe until the test. Okay, I'm joking. Have a good break, guys.